All right, today we're going to run through a 3D statics problem, but before we actually jump into the analysis, what I want to do is provide some background physics and theory that's going to drive our analysis forward. Now, statics is a pretty straightforward, easy discipline, but if you have not heard of it before, what exactly does it mean? As the name implies, statics is the study of systems that are not dynamic. They're in equilibrium. In other words, it has to do with systems that are not in motion. Now, when you hear that key word or key term, not in motion, what does that actually imply? That implies that the velocity of the system is zero and the acceleration also is zero. That has very important implications, and it can help us restrict the different solutions pertaining to a system. What actually does that mean? Well, if we take a look at Newton's second law of motion, which asserts that F equals ma, and we know that the acceleration is equal to zero, this can allow us to assert that any system in static equilibrium is going to have all forces acting upon it sum up to equal zero. This allows us to assert that the sum of the forces on that system equals to zero. Furthermore, it also allows us to assert that since that system is not moving in a rotational sense, in addition to a translational sense, we can also assert that some of the moments or torques on that system are equal to zero, right? Because normally we say that the sum of the moments is equal to the moment of inertia I times the angular acceleration alpha. In this case, if it's not rotating, if it's restricted to have no motion whatsoever, then we can assert that the sum of the moments equal zero. And that's it. That's the underlying physics that drives any kind of statics analysis forward. Now, I know what you're thinking. That's super easy. That's super straightforward, and I agree with you. My statics professor would actually assert many times in class that statics is super, super easy. The way in which statics becomes extremely difficult is in the accounting department, right? We have to keep track of our variables, we have to keep track of our equations, and we have to be organized, okay? So that's going to be the name of the game that's going to drive our analysis forward in this problem. So let's jump into it. Before we do that, make sure you hit that like button, subscribe to our channel if you have not already to get updates on new videos, new problems we solve, and make sure you smash that notification bell. I hope you enjoy the video. Let's jump into it. All right, so now that we've covered the underlying physics that are going to drive any kind of statics analysis, let's actually jump straight into the problem of solving a 3D statics problem. So the problem statement is as follows. It states, suppose that the corner of some electrical conduit, if you don't know what conduit is, that's sort of like a hollow metal tube that guards electrical wire in an industrial setting. But suppose that you have some of this electrical conduit and it consists of 3 tubes welded together as shown below in this nice diagram right here. The conduit is supported by 3 smooth collars at A, B, and C, which prevent displacement normal to the axis of each respective tube. So that's very similar to what you'd find with something known as a journal bearing, very similar. If a load of P equal to 400 newtons is applied to this system, determine the resulting reactions at A, B, and C. The dimensions lowercase a, b, and c are as follows in the diagram below. A is equal to 0.5 meters, b is equal to 0.4 meters, and c is equal to 0.45 meters. All right, so the first thing you want to do when you solve this kind of problem is, as I said, statics problems, you got to be organized. So we want to organize everything on a nice free body diagram, okay? So the diagram we have here is already pretty nice as is, but I'm going to draw a new free body diagram. And I'm going to try and make it nice. I'm not the best at drawing, but we'll make do. So we're going to have some tubing like this. It's going to go over like that. And then we have a portion that goes straight up like that. And now the next thing you want to do is you want to figure out what's going on at these joints, A, B, and C. Okay? So if any system is in equilibrium, you need some kind of reaction force that's either going to hold it up or prevent it from rotating, okay? So in this case, when you have something that's similar to a journal bearing, think about this. If you have a tube and you have a ring, you slide it through, something like this, like that, right? It can sort of rotate still, but it can't go up and down, and it can't go forward and back. So there are restrictions in 2 dimensions. It can't go up and down in the plane along that ring, and it can't go forward and back. So at each joint, we're going to have to impose unknown reaction forces that we're going to have to solve to keep this thing in static equilibrium and prevent, what is it? Motion, as we talked about. So let's go to each joint. So first, B. So we look at B, and what we want to do is we want to figure out the axis system for this journal. What plane is running through this ring here? So we know that the ring is in the X and the Z direction, so we're going to have reaction forces that oppose motion in those directions. So let's write that in. So first we have B in this direction, which is parallel to the X axis. So we're going to call this reaction force simply a BX reaction force, and this is a force, so I'm going to put a vector notation in as such. And this also prevents motion in the Z direction as follows. So we're going to have to also put a reaction force like such, BZ, and I'm going to put a little vector notation as such. So that's going to be the reaction forces at Z, rather at B. We're going to want to do the same thing for A. So let's figure out the plane that is parallel to this ring. So the plane is going to be in the Y direction and the Z direction. So again, we're going to have reaction forces in those directions. They're going to prevent motion of the bar that's running through it. So we're going to write a vector or a force vector. We're going to call it A. This one is going to prevent motion in the Y direction. And we're also going to have to prevent motion in the Z direction. So we're going to have to write a guy like this, parallel to the Z axis, which is going to be A, Z, and we're going to put a little vector notation on that vector. So the final one left is the reaction forces at Z. Again, we want to figure out the plane that is parallel to this ring. We know that plane is going to be in the Y direction and the X direction. All right, so that results in vectors, or rather reaction forces, C in the Y direction, and also C in the X direction. And before we proceed, it's very important we put down an axis system. So I'm going to put a little guy right here. So this is going to be X, Y, and Z to keep us straight in terms of what we're doing. So we see that if we cross X into Y, we get a vector that's coming out towards me. So that's going to be the Z. So this guy makes sense the way it's actually set up. So the next thing we want to do is, we're told right here that we have these dimensions and we want to make use of them. So I'm going to actually draw them in here to make sure that we're organized with the problem at hand. So we have an A term right here, which is extending out from that guy right there to A right there. So I'm going to make a little dashed line if I can, as such. And we're going to do that. So we're going to have some kind of distance over here. And this is going to be, this is an A, so I'm going to write in the actual dimension, 0.5 meters. And we're going to do the same thing with this C guy right here. So the C guy is sort of coming out like such. And this guy is going to extend out a little bit. And we're going to write that guy in. So what is this? This is C. This is 0.45 meters. And then we're going to do the same thing for B, which tells us that we have to extend this guy out a little bit, and stuff is sort of getting in the way, but we'll make do. So this is going to be a B, and this is 0.4 meters. Okay. So the free body diagram is the first thing you want to do to keep yourself organized, to write in your reaction forces and sort of give you a diagram to use when working through this. The next step is to collect all of your equations and your variables. So in statics, as I just said, the two main equations you have are the sum of the forces in the x, y, and z have to be equal to 0. We're constraining motion translationally in all directions, at least in the Cartesian frame. And we're going to restrict rotational motion, so the sum of the moments in x, y, and z along those axes must equal 0. So that means that we get 6 equations, and that means that at most we can have 6 unknowns to actually solve the problem. So if we have 6 equations and we end up with more unknowns, that means that the problem is statically indeterminate. We cannot actually resolve the problem. We can actually come up with a solution. We can't come up with it. So what you would have to do is you have to go back to the physics and try and come up with a new physical relation that can restrict your solutions down so it can be solvable. In this case, we have 1, 2, 3, 4, 5, 6. 6 unknowns. So we're good here. We can actually solve this. It's statically determinate. So what we want to do is actually apply those equations. So let's do just that. So the first one we're going to apply is we're going to take a look at the easy stuff, which is the forces in the x, y, and z axes. So what we're going to say is we're going to say that the sum of the forces first in x is equal to, well, we look here, luckily we labeled out all the different forces here. So we can take bx and cx. So this becomes bx plus cx. Cx, sorry about that. All this is going to be set equal to 0. Why? Because there's no motion, there's no translational motion. Okay, so that's our first equation. And then number 2 is our next one. So next we want to do it in the y-axis. Same exact game we're playing right here. So we look at our diagram, we see cy and ay are in the positive direction. So we end up with an ay plus cy equal to 0. All right, let's keep chugging along. So next, as I already mentioned, we have a sum of the forces in the z direction. And again, we just look at our diagram. So z direction is positive right here. We see we have an az and a bz. So we get AZ plus BZ equal to 0. And if I back up a little bit, you probably may have noted as we ran through these equations that I picked these vectors to be positive for a reason, right? I could have assumed, based upon looking at this direction, that they may be in a certain direction. Maybe I have bx in the opposite direction based upon how I think the reaction of this sort of journal bearing would react upon this system. But what I've decided to do to make the math easy and straightforward is I'm assuming that everything is in the positive direction. So if we find that everything is negative, I don't have to think about what direction those forces are in, and I can just flip it to the opposite direction, okay? So it's a bit more intuitive, and what you have to do is you want to come up with some kind of system that allows you to keep things straight, okay? Again, statics is all about organization and accounting, okay? So you want to come up with a system that works for you. This is the one that I've chosen. I think it works really well. Feel free to adopt that if you want. So, chugging along, next we want to do is we want to restrict rotational motion such that this guy is in static equilibrium. So the first thing we're going to do, we're going to pick a point that we want to sum our forces around. And I'm going to pick B for a reason. You can pick B, C, or A. I've picked B in this case. And the reason why we want to pick it at one of the locations here is because if the lever arm to our reaction force B is 0, that's going to cancel out the moment that actually ends up in that equation, okay? So what I'm going to do for number 4, I'm going to sum the moments at B along the x-axis. So what this is saying is the moments, basically the forces and the lever arms between them where they're applied are going to act in such a way that it tries to rotate this guy around the x-axis. So it's sort of like rotating as such around that guy right there. So that means that, okay, I guess I'll write it up. If you have some kind of moment, a moment is sort of like R cross F. In order to have a value in the X direction, right, your force must be either in the Y or the Z direction, and your R must be in the Y or the Z direction, okay? So looking at the diagram, we can see here that we have a Y force, and that is offset by a distance in the Z direction. So we see that's going to have a contribution. And if you're having a hard time seeing this, you want to think about, you can use the right hand rule. You can sort of use your palm right here as the lever arm, and you want to move that down in the direction and then curl in the direction of the force. So in this case, we're going to move in the Z direction. We have a force in the Y. Our thumb goes in the X direction. That's going to yield a force due to the CY. And it's going to be in the negative direction because our thumb points to the left in the negative direction. So we're going to get a negative 0.45. So we get a 0.45. We get CY. And then we're going to have another term. The term we're going to have is actually AZ, because you want to think about, we're moving down in the Y direction, and then we have a force in the Z direction. So you go down, you pull in the Z direction. That gives you your thumb going in the negative direction. So that gives a negative 0.4 AZ equal to 0. All right. And what I'm going to do now is I'm going to backtrack a little bit because I noticed that I forgot to draw something in my free body diagram. And this is a lesson for you. If you don't, right, this is really easy physics. But if you don't account for everything in your free body diagram, you're going to forget that. It's not going to crop up in your equation, and you're going to get the wrong result. So what you want to do is, look, there's a P guy right here. So we need to apply a force that's going down, which is 400 newtons. And what happened was, I'm going to erase this guy right here. So yes, in the Y direction. So we get AY plus CY, and then we have a negative 400, which has to end up on the right. So we plus 400, and we get a 400 Newton value on the right here, all right? So you got to make sure you don't forget that, because that can cause problems in the future. So next, what I'm going to do, I'm going to pop up right here, and we're going to take a look at the next some of the forces problem, or not some of the forces, some of the moments. So we already covered the moments around the x-axis. Next, what we're going to do, we're going to take the moments at the same point in the y direction. And what we want to do is we want to look again at our free body diagram. It's a bit harder than the forces, but we can take a look at, again, the forces and the lever arms and pull them together to end up with our moments. So let's take a look at that free body diagram. All right, so the first one I see right away is this CX right here, because it's pointing in the X direction, and we need a lever arm in the Z direction to create some kind of Y moment along that axis. So what we see is that C is in the X direction. We have this 0.45 in the positive Z direction, and so it's coming towards me. We curl in the X direction. That gives us our thumb pointing in the Y direction. So what we end up with is a positive 0.45 CX. That's a 0.45 CX. And then next we have this AZ, which is the force in the Z direction. We have a lever arm in the X direction, so that's going to create a moment along the Y axis. And the way what you want to think about this is you're moving in this direction, you're curling out like this. That makes you point down along the y-axis, so you get a negative value. So that ends up with, let's see, so negative 0.5. Here's the lever arm, negative 0.5 AZ. All right, so we're making good progress here, and all we really have left is just one more equation that we have to produce in order to restrict our system and have a statically determinate problem. So number 6. Number 6. So what we're going to do is the last axis, which is sum of the moments at B in the z-axis. And all we need to do is, again, just take a look at our free body diagram right here. So we're spinning around this axis. And what do we have? So we have the AY. So that should have an X lever arm to create a Z moment. So we see that if we go over 0.5, this guy down here, we go over, we curl in the Y direction. That gives us our thumb pointing in the positive Z direction. So that's going to give us a 0.5 times AY. So that's a 0.5 AY. And then what do we have next? We also have this CX force, which is pointing in the X direction, and we also need some kind of lever arm for that. So if we have a lever arm in the Y direction, that's going to create, again, a moment along the Z axis. So what we do is we see that we go down in the Y direction, 0.4. We move in the X direction. That gives us a positive rotation along the Z axis. So we get a plus 0.4 CX, and of course that is all equal to 0, just like we should have had right up there. So once you have all of your equations of motion, which have all the information you need for solving this problem, what you want to do is you want to organize everything. Again, statics is about accounting. So what I like to do, you could solve all these equations for each variable, but what I think is better from an accounting standpoint is to transform this system into a matrix equation. So I want to collect all these guys and transform it into a matrix equation. And the first thing you want to do is you want to group all of your vectors into a column vector, okay? So what I'm going to do is I'm going to first do the A's, then do the B's, then do the C's. So looking at our free body diagram here, we have an AY, we have an AZ. For the B guys, we have a BX, we have a BZ, we have a CX, and we have a CY. All right. So that is our column vector. And next, what we want to do, we just look at each equation, and we want to form a matrix equation. Okay. So the first equation. We don't have any A's. We don't have any Z's. So what we end up with is 0, 0. We have a BX. That's going to give us 1. We don't have a BZ. We have a CX. That's going to give us a 1. We don't have a CY. And that's about it. So the way in which this works is when you have a matrix, and I'm going to put in the right side right here. I'm going to leave the bottom untouched. Your matrix like this, what you do is you take the row and you multiply by the column. So this is no different than equation 1. And I guess I'm going to check this guy off. So we got this guy. So this says 0AY plus 0AZ plus 1 times BX plus 0 times BZ. That's the same equation we had. And that is all equal to what? That's equal to 0. Okay? So next, let's jump to equation 2. So we have an AY, so that's going to give us a 1. We don't have an AZ, that's another 0. We don't have a BX. We don't have a BY, or sorry about that, a BZ. We don't have a CX, but we do have a CY, so that gives us a 1 there. And that is all equal to 400. Okay, so I'm going to check that guy off. We accounted for that guy. Let's continue. So we look at equation number 3. So we don't have an AY. We have an AZ. We don't have a BX, but we do have a BZ. And then all the other guys are 0 because we don't have any C terms. Now, when we get into the moment equations, it's going to be not as nice. But we can still work through it. We can make this work, guys. We can make this work. So first, we want to count for the A's. We have 0 for AY, AZ, we have a negative 0.4. The B's, we have 0, 0. We do not have a CX. We do have a negative 0.45 for CY, and that is all equal to 0. Okay, so we're done with this guy right here. And we want to look at equation number 5. So we do have an AZ, but we do not have an AY, so this guy is 0. The AZ is a negative 0.5. We don't have any B terms, so they're both 0. We do have a CX, that's a 0.45. We don't have a CY, and that's all equal to 0. Okay. Now, finally, we want to take a look at equation number 6. So that does have an AY. That's actually 0.5. We don't have an AZ. We don't have any B terms. We do have CX, which is 0.4, but no CY. And all that is equal to 0. So we have this nice matrix right here. So now I know what you're thinking. You're probably looking at this and you're like, whoa, what exactly did we gain here? It looks much more complicated than the equations here. And the reason why this is beautiful is because we can come here, we can say this guy, this whole thing is going to be a matrix we're going to call A. And we're going to call this guy a column vector we're going to call X. And then we're going to call this B. Okay? So what we can do is we can come up here and we can say, well, if we have this matrix A times X equal to B, well, this is easy to solve because all we need to do is, in order to get this, is this guy right here. We just need to take the inverse of that guy, right? Because if we multiply by the inverse on both sides, A negative 1, A times X is equal to A negative 1, B. Well, what is this guy? This guy right here is nothing more than the identity matrix, right? So the identity matrix times X, well, that's just like multiplying a vector by 1. So you get X is equal to A negative 1, B, and this is where the accounting just becomes beautiful, right? Because you just have to take everything, throw it into a matrix, find this inverse, right? This inverse right here, this is the key. Multiply by your B vector, and that didn't come out very nice, sorry about that. And then you have your end result. But getting this inverse vector is quite tricky, and I would recommend throwing it into MATLAB, Mathematica, whatever you want to get the end result, and that will allow you to proceed. All right, so what I've chosen to do so as not to bore you guys is to actually evaluate the inverse of this matrix A in Wolfram Mathematica, and I get the following. So again, what we're trying to do, we have AX equal B. We want the inverse of A, multiply by both sides, and then we can solve for all variables that are in the column vector X. So the inverse equation I get here, or the inverse matrix, is as follows. I get this big guy over there, and I have to take B, which was basically the right side of our matrix equation. So that guy is right there. And all we need to do is just use matrix multiplication, and then we get the end result. So in essence, we could do that right here. I can walk you through that. Basically, you go row, column for the first entry. So that's 0 times 0 plus 0.5 times 400. That gives us the 200 right here. Everything else is multiplied by 0. It ends up as 0. That's the final result for AY. All right, so we could do the same exact thing over here. So we end up with 0 times 0, that's 0. Negative 0.5625 times 400. Turns out that gives us a negative 225. Everything else is multiplied by 0. It cancels out, okay? So again, the whole thing here is we only are concerned about this column here because everything, when you multiply it out, it's going to multiply by zeros. So again, 1 times 0 is 0. 0.625 times 400. What is that? That gives us 250 right here, positive 250. Everything else is going to be 0 out in there. The next row, we have a 0 times 0 plus 0.5625 times 400. We saw previously that was a 225, but this time we have a positive term here. So we end up with a 225 there. The next row, what we end up with is a 0 times 0, that's 0. A negative 0.625 times 400. That gives us a negative 250, similar to what we saw up here with the bx term. But we have a negative 250 for cx. And finally, the last row, we have 0 times 0 plus 0.5 times 400. That's going to give us 200. And we get up the end result right here. All right, so this is the beautiful result we've been waiting for, we're looking for. So we're excited. We're going to circle that in our Galaxy ink because we're making a dent in the universe with this result. This tells us that if we go back to our free body diagram, AY is in the same direction, has a magnitude of 200. But for example, if we have a negative quantity such as AZ, that's negative 225, we assume the wrong direction. So all we have to do is, we know that the solution is actually in that direction right there. So that is actually AZ. So it's actually in that direction as opposed to the one we observed here. The only other guy we have to do that for is CX, which is actually in that direction right there, CX. All right, so that's that. It's a very simple, straightforward analysis. Most statics problems are, right? The physics is easy. You just have sum of the forces equal to 0, sum of the moments equal to 0. But the challenging part is really accounting for all the different variables, your equations, keeping track of everything, and staying organized. Now, I know some of you out there are thinking, well, wait a minute. The way in which you solve this is sort of a cop-out. And you're right. I did make use of mathematical programs, and that's mostly because trying to find the inverse of a 6x6 matrix, which is what we're dealing with, can be pretty convoluted, and you want to avoid that at all costs. It takes a lot of work, a lot of computation. So what I actually recommend is the first time you work with linear algebra, which is super important and an effective tool for statics, what you want to do is you want to find the inverse of a simple matrix. Start with 2 by 2, do 3 by 3 at most, and become comfortable with the ideas behind that. And what you would want to do is really program that up in MATLAB or even C. It's really a problem for a computer science student. If you have any computer science students out there, this is a problem for them or for you if you're a computer science student. But I would not recommend actually solving this by hand, and I'm not going to do that because it would be just a nightmare doing it on the tablet that I actually have. Another way of doing this, and I can cover this if you are interested, is by using a Gauss-Jordan elimination. That's an idea that's usually taught at the beginning of linear algebra, and it involves trying to reduce a matrix into reduced echelon form, which is basically having the diagonals as ones, all the terms to the bottom left of it as zeros, and that allows you to read off the solution quite quickly. I'm not going to do that in this video because it would just be a nightmare just keeping track of everything on the tab. But if interested, I could go over that in a separate video. So make sure you leave a comment below in the comment box. And if you have not already, make sure you like the video, subscribe to our channel for additional videos. And if you have a problem you want me to solve or any kind of topic you want me to talk about, make sure you send an email to ed@thekaizeneffect.com. Trying to collect problems that you guys want me to solve for free. Yes, for free. I can do that and guide you along with it. I'm experimenting with possibly doing live streams. If you want a live stream where I can work through it with you one-on-one, let me know and I can get that started and we can have some fun. So I hope you enjoyed the video. I hope you learned a bit, and I hope it was fun working through the statics problem. It's pretty easy. It's just a lot of math and a lot of accounting. All right. Stay tuned for future videos. Thank you.